Hello, this is a recording for the lecture on Chapter 9, Thermochemistry. We will only be covering sections 1 and 2 of Chapter 9 for this particular, for the thermochemistry chapter. We're not going to go into any more detail. Thermochemistry is that part of chemistry that studies the exchange of heat. Losing heat or gaining heat. Heat is a form of energy, and we will define energy as the capacity to supply heat or to do work. In our case, we will focus mostly on the capacity to supply heat. That will be the definition for energy that we will work with. So energy is the capacity to either supply heat or do work of some sort. If I have two objects that are at different temperatures, one is a hotter object, one is a colder object, there are several things that just even by experience we'll be able to see and say. First of all, is that the hot object obviously has higher thermal energy than the colder object. And if we were to look at the particles in that object, the hotter object, we will see that they are moving faster. Therefore, they have a higher kinetic energy. The particles in the colder object are moving slower because they have lower kinetic energy, because they have lower thermal energy. These two terms are related, directly related to each other. The higher the thermal energy, the higher the kinetic energy. The lower the thermal energy, the lower the kinetic energy, or the slower the molecules are moving. That is also true. Now what happens, so I have a hot object and a cold object. What happens if I put these two right next to each other, touching, in contact with each other? Well, here's what will happen. First, I have the hot and cold object separated. Now, if I put them in contact with each other, what's going to happen is that heat is going to flow from the hotter object to the cooler object. Once again, this is something that we all know from experience. It's going to flow until both of these objects reach what is called thermal equilibrium. They have the same amount of thermal energy, which translates to the same temperature. These objects, they started out one hot and one cold, and they end up at the same temperature because the hotter object transferred heat or energy, thermal energy, in the form of heat into the colder object for as long as they were at the different temperatures. Once they hit the same temperature, there is no more heat transfer because they have reached the same thermal energy. There is no difference in the amount of energy that they have. Therefore, the heat flow is zero. And then the temperature is the same. This is always true. We know that just even by touching hot or cold objects, we know it by our experience. So if I'm touching, let's say, a warm hot water bottle, well, I know that it's hot. And how do I know that? It's because, well, its temperature is higher. As I touch it, I notice that it's hotter. What happens is, because it's hotter, it has more thermal energy, and when I touch it, some of that thermal energy in the form of heat is passing into my hand, which increases the temperature of my hand, and that therefore my brain interprets that as, oh, this object is hot, because I am sensing a heat flow into my hand. The opposite is true. If I touch a cold object, the heat exchange now is from my hand to the cold object, because I am the object with the higher thermal energy. So heat always flows from the hotter to the colder object. And my brain interprets that as, oh, I'm losing heat, and therefore the object that I'm touching is colder. Heat is always therefore transferred from the object with a higher thermal energy or higher temperature to the lower thermal energy or lower temperature. They will continue, the heat flow will continue until thermal equilibrium is reached, and the difference between thermal energies between these two objects is zero, and therefore there's no more heat flow. How do we measure the heat or thermal energy? We measure heat in two different units. One, which is the classical unit, is the calorie. But because it depends on the pressure, the atmospheric pressure, and the initial temperature of the water, we don't use it in the SI unit. Although it is still very widely used because it's very easy to do, it's very easy to measure. However, in more specific science experiments, we don't use the calorie, we use joule. And this is what we're going to be using when we do our calculations, the problems that we're going to be doing. But 1 calorie is defined as the amount of heat that is needed to raise the temperature of 1 gram of water by 1 degree Celsius or 1 Kelvin. It doesn't, in this case, they're interchangeable because it's a difference. It's a final minus initial temperature, not an absolute temperature. So the difference is the same in degrees Celsius as it is in Kelvin. So for these types of problems, though, we are going to be using mainly the degrees Celsius. I know that in chapter 8, I said that we're going to use Kelvin, only Kelvin, for the gas laws. But in chapter 9, we're going to be using the degrees Celsius. Keep track, please, otherwise it will confuse you in the problems. 1 calorie then is also defined as 4.184 joule, which is the SI accepted unit. The joule is named by the scientist with the same name. It's named after him, and is defined as the force of 1 Newton moving an object by 1 meter. So it's an amount of work as well as energy. So the joule is used for work, energy, and heat. And it's defined as 1 kilogram times meter squared divided by second squared. We're not really going to deal with this much. You just have to see that this is what 1 joule is. We're going to be using mainly just joules. How does heat vary by substance? Okay, we talk about the specific heat capacity, little c, or specific heat. The specific heat is dependent on the type of substance that is measured. So every substance has a different specific heat capacity. That's why it's called specific. And obviously it depends on the particular substance. It's defined as the amount of heat that is needed to raise the temperature of 1 gram of that substance by 1 degrees. Do you see now that it's a temperature change, so final minus initial temperature, and therefore it's not an absolute temperature. It's got this delta in front of it. So it can be measured in Kelvin or in Celsius, but we will measure it in Celsius mostly. Specific heat, as I said, once again, is specific for every substance has their own specific heat capacities. Most substances have a low specific heat. Water has a very high specific heat in relation to other other substances. So C is very high for water, it's 4.184. That is, what does that mean? It's a good thing for us. That means that it takes water a large amount of heat to raise its temperature by 1 degrees, whereas it may take other substances very little heat. So they fluctuate in heat, in temperature and in heat a lot, whereas water doesn't. The good thing about that is that all of the water in the oceans that we have allows, it traps this heat from the sun, so it tempers the temperatures that we experience. Otherwise, we would experience a large amount of shift in temperature day and night. But that water is what allows us to have those temperate temperatures, so not huge temperature fluctuations. So specific heat is the amount of heat that is needed to raise the temperature of 1 gram of substance, that's mass, 1 gram of substance, but by 1 degree Celsius. And it's just a measure to see how some substances require a lot of heat to raise their temperature, like water, and most other substances don't require much heat to raise their temperature. But we're going to be using this in a lot of our calculations that for the problems that we're going to do. Here's examples of those types of calculations where we're using Q equal mc delta T. So if I isolate Q, I multiply both sides by m delta T to get rid of this, and I'll have m delta T up here. So mc delta T is equal to Q. That we'll be using a lot for these types of problems. Now, I am not going to talk about these here because I've made separate videos on each of these problems that I have uploaded links to on JetNet. You can print this out so you have it and read it as I am solving each of these problems, and you can follow along. I've done it for all these problems in Chapter 9. Now, how do we measure the heat transfer? We measure it through a method called calorimetry. Calorimetry measures the heat transfer from one object that is hotter to another. Now this is, I know the amount of heat that's required to change the temperature of the calorimeter itself. So if I know that, and if I know the specific heat of the calorimeter, and I know the mass of the calorimeter, if I know the mass of the water and specific heat of the water and the temperature change, I can then figure out specific heat for any other objects that I drop in here because everything else is known. And I'll show you how to do problems on that separately on JetNet too. The calorimetry measures the heat transfer, and we have two types of either, reactions or physical changes. One that releases, so anytime you have heat that is being released during either a chemical reaction or when we have a physical change, we call that an exothermic event. So either an exothermic reaction, if there's a chemical reaction occurring that releases heat, or an exothermic physical change. So if there's a physical change that occurs that releases heat, that is also an exothermic change. The opposite is true. So for an endothermic reaction, if heat is absorbed in a chemical reaction, that means that we have an endothermic reaction or endothermic physical change. Those are the two types. So exothermic, exo meaning out, releases, endo meaning in, it absorbs. So those are the two types of chemical reactions or physical changes. So exothermic releases heat, endothermic, it absorbs heat. And how do we, so let's look at exo and endothermic reactions or physical changes in terms of two different quantities. So we'll specify two different variables here. We have what is called the system and the surroundings when we deal with calorimetry. The system is whatever is taking part in the chemical reaction or in that physical change. The surrounding is everything else around it. That's why it's called the surroundings. In general, it is a solution along with a calorimeter. So if I have in part A, if I have an exothermic change, what will happen is that the system is going to supply heat to the surroundings. And because I have a thermometer here measuring the temperature of my surrounding, I will see an increase in temperature because the surrounding is absorbing that heat. I have the heat flow from the hotter object to the cooler object. The temperature is going to rise, and it's going to rise by a certain amount and no more. And when that happens, when the temperature increases to a certain point and it doesn't change anymore, that means that my system and my surrounding have reached thermal equilibrium, so there is no more heat being exchanged between the two. What happens in an endothermic process? In an endothermic process, my system is at a lower temperature or has less thermal energy than my surroundings. Therefore, the energy or the heat is going to flow from my surroundings into my system. And as it does that, because my temperature, my thermometer is measuring the temperature of my surrounding, I will see a drop in temperature. My temperature is going to drop because the heat is leaving my surrounding to go into the system. Therefore, the temperature is going to drop. This is going to continue until the system and the surrounding, reach thermal equilibrium, meaning they're at the same temperature. Once they reach once they reach thermal equilibrium, the temperature doesn't change anymore, and there is no more heat flow. So this is a picture of an exothermic process. This is a picture of an endothermic process. Now it depends on where you're looking, what you're looking at, what you're measuring. Here I'm measuring the temperature of the system, of the surrounding in both cases. And so in an exothermic process, the temperature of the surrounding increases, and in an endothermic process, the temperature of the surrounding decreases. The opposite is true for the system. So if I look at the exothermic process, but I look at the system, because the system is losing heat to the surrounding, that means that the system's temperature is dropping. The system's temperature is going to drop until it reaches the same temperature of the solution, which is being increased. So this is a hot object, this is a cold object. The temperature of the system is going to decrease while the temperature surrounding is going to increase till they reach a certain temperature. The opposite is true for the endothermic process. Take a moment to look at this and be able to tell yourself which direction is heat flowing in this exothermic process, what's happening to the temperature of solution, what's happening to the temperature of the system. And do the same for the endothermic process. Just get them clear in your head and solidified. This is the logic then behind calorimetry problems. Because we have the conservation of energy, meaning energy cannot be destroyed nor created, that means that the heat of one system, so heat of my sample, it could be a metal, whatever it is, and the heat of water typically, The sum of these two is going to equal 0 because that's what the law of conservation of energy says. They don't, energy does, it's neither created nor destroyed, which means that these two have the same value, but they have opposite sign. There's the opposite sign right here. Which means one of them is going to lose heat, one of them is going to gain the heat. But that heat that is transferred, that energy that is transferred, is not going to be lost to anything else. The amount of heat that one loses is equal exactly to the amount of heat that the other one gains. Now, this isn't exactly true, but because of heat loss to air and other parts, but it is minuscule, and so we can approximate that these two are equal. Now, I know that each of these can be expressed in these terms. The mass of my sample times the specific heat of my sample times delta T, the change in temperature of my sample. That's equal to the negative of the mass of my water in this case times the specific heat for water times the delta T, the temperature change for water. The temperature changes are going to be different. If water starts out hot and it cools off, this is going to be a negative delta T, which takes care of that negative up front. Whereas if you start up cool and you at a lower temperature and you gain heat, therefore the temperature goes up, your final temperature is larger than the initial temperature. So this delta T for my sample is going to be a positive number, which makes this a positive number as well. Now I can substitute the delta T by T final minus T initial for both the sample and the water. And don't forget, you still have a multiplication sign in front of these two parentheses right here. I have used these formulas in detail to do the rest of, so slide 12 and slide 13 are full of problems, and I have used these formulas to show you how to do these calculations for the rest of these problems. If you have any questions, please don't hesitate to email me, as well as we will have blue button sessions for these this chapter. So bring your questions there, and I will help you figure out how to do these problems. Okay, thank you and have a good day.